The NASA's Curiosity Mars rover has just made a stunning and truly mind-blowing scientific discovery on this distant and mysterious red wasteland. If you still envision Mars as a dusty, lifeless, and hostile barren planet, then it's high time you perked up your ears and listened attentively. The Curiosity Mars rover has been silently exploring the Martian surface for years. Now, it has detected a series of astonishing molecules. These complex organic compounds may very well imply a biological origin. So, what earth-shattering secrets has the Curiosity rover unearthed on this red planet? And why could some seemingly simple hydrocarbons potentially revolutionize our fundamental understanding of the existence of extraterrestrial life? Please make sure to follow through to the end, because perhaps this time, the Curiosity rover has truly opened the very first door that could reveal the existence of life on Mars. After all, this question has been deeply ingrained in our souls ever since humanity first looked up at the starry sky. Are we truly alone in this boundless universe? Among the thousands upon thousands of celestial bodies in space, could Earth be merely a fortuitous occurrence rather than an inevitable wonder? To solve this mystery, today's scientists have already employed technological marvels like the Webb telescope, focusing on those distant exoplanets and searching for the faint signs of life hidden within their atmospheres. However, who can say for sure? Maybe in the end, we don't have to cast our curious gaze millions of light years away. Because if real extraterrestrial life has been quietly slumbering on a neighboring planet right beside us, indeed, if there is any celestial body in the solar system that has long been suspected by the scientific community of potentially harboring groundbreaking secrets, there is no doubt that it is Mars. And what we're talking about here is by no means some fantastical speculation like ancient Martian civilizations. Instead, it stems from the extraordinary insights derived from the long-term, rigorous, and systematic scientific exploration carried out by the Curiosity Mars rover. Specifically, this Mars rover, equipped with advanced laboratories, is roughly the size of a small SUV and weighs nearly 900 kilograms. Since its landing in 2012, it has been tenaciously searching for every trace amidst the rugged terrain and variable climate conditions on Mars. In 2018, the Curiosity rover achieved its most significant scientific breakthrough to date. It provided the first exhilarating direct evidence that there do exist a rich variety of complex organic molecules in the Martian surface rocks. These substances are the essential building blocks in the chemical chain of life. The miniature chemical laboratory on board the Curiosity successfully detected a variety of important molecules, including cyclic hydrocarbons, chain hydrocarbons, and organic sulfides at four carefully selected sampling points in Gale Crater. However, this exciting discovery also comes with a huge and disheartening caveat. Regrettably, scientists are still unable to confirm with 100% certainty that these organic molecules were directly produced by life activities rather than synthesized through other chemical pathways. Indeed, on Earth, most similar organic molecules originate from life processes, and their isotopic signatures often point to a biological origin. But the scientific community is also well aware that certain abiotic processes, such as ultraviolet radiation or inorganic chemical reactions, can also generate these molecules without the involvement of life. Therefore, although these molecules are exciting, strictly speaking, they cannot be considered conclusive evidence of the existence of life on Mars in its early days. So, what has the Curiosity rover discovered on Mars this time? Why has this new discovery once again shaken the global scientific community and topped the astronomical news headlines? To be precise, this new discovery is the result of a detailed chemical analysis of a batch of clay samples collected from the Cumberland mudstone in Gale Crater by the Curiosity rover. During the operation, the chemical experimental equipment of the Curiosity first heated these phyllosilicate samples to 450 degrees Celsius and then further heated them to 850 degrees Celsius to decompose potential organic components and conduct precise analysis using a mass spectrometer. To enhance the sensitivity of the analysis, Dr. Frizon Rotter from the Sorbonne University in France and NASA scientists specifically improved the chemical detection process, enabling the instrument to capture even longer chain organic molecules. Fortunately, this technological upgrade achieved the desired results. The Curiosity successfully detected guanine, dodecaine, and tetradecaine in the samples. That is to say, it discovered 3 typical long-chain alkane molecules. The concentration of these alkanes was precisely determined to be between 27 and 53 parts per billion. Although extremely trace amounts, in the extreme environment of Mars, this is of great significance. It is particularly worth noting that these are the largest molecular weight and longest carbon chain organic substances ever detected on the Martian surface. And the members of the scientific team responsible for this study also stated at a subsequent press conference that this new detection significantly expands the diversity of the known types of organic molecules on Mars. This is not just a simple technical triumph. More importantly, it shows that even under the extreme conditions on the Martian surface, which have long been subjected to intense radiation and extremely high oxidation, complex macromolecules can still tenaciously survive. Even more excitingly, this achievement not only rekindles the scientific community's hope of finding ancient biological traces in Martian clay rocks, but also holds unique significance in another key aspect. Because the alkane molecules detected by the Curiosity may not have been formed in isolation, but could be the remnants of ancient life forms, such as the long-chain fatty acids in the membranes of ancient cells, after undergoing complex physical and chemical changes over a long geological period. In this regard, Frizong Betty and his colleagues, through meticulous laboratory comparative studies, have put forward an exciting hypothesis. The alkanes detected by the Curiosity may have originally existed in the form of long-chain carboxylic acids with a carbon chain length of 11 to 13 atoms in the ancient clay rocks. That is to say, only when these carboxylic acids are heated at high temperatures in the experimental device of the Curiosity are the alkane molecules that we detect now formed. But what does all this mean? The scientific significance behind it is far more complex than it appears on the surface. In other words, can these thrilling discoveries really prove that Mars once harbored life? Certainly, this most central question has long become the focus of in-depth discussions and debates within the research team, leading to the following preliminary conclusions. According to current research, the presence of guanine, undecane, and dodecane, these 3 long-chain alkanes, likely originates from long-chain fatty acids such as palmitic acid, stearic acid, or oleic acid, which are prevalent on Earth. Under specific geological conditions, these fatty acids can decompose to form similar alkanes. In biology, such fatty acids are often regarded as potential biomarkers, a detail that demands our utmost attention. If this hypothesis is conclusively proven in the future, it would mark humanity's first discovery of chemical remnants of life beyond Earth, representing a pivotal step in confirming the existence of extraterrestrial life. Thus far, the findings sound spectacular, worthy of being labeled a milestone in scientific history. However, experts remain cautiously reserved, resisting the urge to celebrate prematurely. As French scientist Fressinet clearly pointed out, the mere presence of aromatic and aliphatic organic molecules still cannot definitively distinguish whether they stem from biological activity or purely abiotic chemical processes. Theoretically, even without biological intervention, complex long-chain alkanes can spontaneously form through abiogenic geochemical processes, a possibility that science must rigorously consider. Yet, scientists also emphasize a crucial fact, as studies of Earth's hydrothermal systems reveal. Abiotic processes typically favor the production of shorter-chain carboxylic acid molecules, while truly complex long-chain fatty acids are extremely rare. Thus, the discovery of numerous long-chain organic molecules on Mars seems to tip the scales subtly toward a biological origin. Intriguingly, life forms on Earth, especially microorganisms, often prefer fatty acids with an even number of carbon atoms during synthesis. Remarkably, the alkanes detected by Curiosity predominantly originate from fatty acids with even-numbered carbon chains, adding significant weight to the biological origin hypothesis. Despite the accumulating excitement from mounting evidence hinting that microorganisms once shaped Mars' environment, the scientific community acknowledges that conclusive proof remains elusive. This uncertainty can be frustrating, but it's clear that with more data in the future, answers will come into sharper focus. After all, Perseverance, another Martian explorer, has carefully collected and sealed precious rock and soil samples from various locations. These samples will return to Earth via the Mars Sample Return mission in the coming years, where they'll undergo unprecedentedly precise analysis, far more detailed than Curiosity's on-site testing. Let's broaden our perspective. Did Mars once host vast oceans? Curiosity's discoveries merely scratch the surface of Mars' potential for harboring life. Recent analyses of Martian meteorites offer fascinating insights, suggesting that during Mars' early days, especially its volcanic period, hot spring systems might have existed. On Earth, hot springs are widely recognized as ideal cradles for early microbial life. Thus, if similar environments existed on Mars, the likelihood of life emerging increases significantly. Moreover, Perseverance recently detected intriguing rock formations on Mars. These dark, bordered imprints are rich in iron and phosphorus. Notably, on Earth, such rock features, known as microbialites, typically form through microbial activity, a classic example of biomineralization. Adding to the excitement, data from NASA's InSight lander's seismic studies delivered explosive news. Analysis indicates that, despite Mars' current desolate surface, a vast reservoir of liquid water exists approximately 11 kilometers beneath the surface. We're not talking about a small puddle. This could be a massive underground ocean system capable of forming a layer 1 to 2 kilometers deep, spanning the entire planet. The scientific consensus suggests that early Mars indeed had extensive surface oceans, but over time, most of the water was lost to space due to the disappearance of the planet's magnetic field and solar wind erosion. But what if this assumption is wrong? What if Mars' water didn't fully escape, but instead seeped deep underground and remains preserved to this day? To address this mystery, a team led by scientist Weshan White from the University of California, San Diego, analyzed seismic data collected by InSight from 2018 to 2022 in Mars' Elysium Planitia region. The results were both surprising and exhilarating. First, the data confirmed that Mars' crust is highly porous, riddled with tiny fractures and voids. More significantly, the behavior of seismic waves indicated that these pores aren't empty but filled with liquid water. Estimates suggest that these subsurface water bodies could account for about 17% of the rock volume in the region, substantial enough to be called natural reservoirs. In other words, the most plausible explanation is that Mars' crust hosts a large-scale groundwater system similar to Earth's aquifers. Of course, scientific rigor demands further investigation to determine if these findings apply only to InSight's location or extend across the entire Martian crust. If the latter holds true, it means Mars' subsurface conceals not just geological history, but also vast liquid water resources essential for life. Perhaps the greatest wonders don't always lurk among distant stars. Maybe they lie hidden beneath the red dust at our feet, silently guarding secrets for billions of years. Curiosity, Perseverance, and countless stargazers are steadily bridging the cosmic divide. Mars may be far from a dead world, it could be a mirror reflecting our past or future. Deep within this ancient planet, time hasn't revealed all its secrets, but it whispers, inviting us to listen, explore, and redefine the very boundaries of life.